Production of Cornell University.
These up at the top there is basically a scale that shows pHs, 5.5 and 8.5. So anything lower than 5.5, we're basically talking about, from an agronomic sense, anything that's below 5.5, we're usually talking about a scenario where we need to add lime. We need to bring the pH up because, remember, it's that active acidity that controls the bases. It's controlling the nutrient dynamics. Okay? So I want to basically have my pH between 5.5 and 8.5 because that turns out to be the maximum zone for nutrient availability. Now, if it's above that, I may in fact have to do some acidification because if I get up to these high pHs, I might start seeing micronutrient deficiencies. It's about nutrient management. Okay. So what are some of the things that we potentially can do? Well, soil pHs shift on this scale due to a number of things. Cropping in humid climates will slowly decrease the pH. Why? If I'm cropping, I'm harvesting, right? And if I'm harvesting, I'm taking the bases out of the system that the plant has harvested from the soil solution. Okay, if I start taking bases away, what's going to have to happen to that relative concentration of protons to bases? The proton concentration is going to start increasing. And if I start removing bases, I no longer have the bases that can exchange on the cation exchange to, in essence, buffer the soil. So as a result, my pHs are going to start dropping. Okay, now the truth is, even if I don't crop and I let it sit there for a couple thousand years, my pHs are going to start dropping because those bases sooner or later are going to be leached out of the system. Okay, pH in arid climates actually increases due to the alkalinity in incoming water. Well, what's going on there? Because of evapotranspiration and the bases being left behind, when I do have water, groundwater moving through the system, or I use water in the system, they tend to have a lot of bases. Okay? So that water is in essence going to be bringing those bases into the soil solution. In arid environments, groundwater tends to have higher pHs, unlike rainwater, which tends to be acidic. Got it? All right. Which brings us into the issue of buffering the soil. We want to control the pH of these soils. We want to basically put it into a certain zone. Okay? And really, what we're talking about is reducing the extreme nature of these events, reducing the extreme changes of pH. We want to slow it down, and we want to basically contain it or maintain it in a certain zone of pH. Does that make sense? Okay. Now, there turns out to be basically 3 different types of buffering reactions. This is, I threw this in here, and I actually already did it over there. But this is the sort of the back to that analogy of the water cooler. This is a large CEC. This is a low CEC. Okay. This pipe right here basically represents the active pH. Okay. And you can certainly imagine, which happened over here, if I have a high CEC that I have 100% base saturation, as I start adding protons into the soil solution, the bases that are on the cation exchange capacities that are in base saturation will exchange and they'll resist the pH change. Okay? In this scenario, I have a much smaller water cooler, which is the one on the right, the scenario on the right. And yes, it will resist pH change, but it has a limited capacity to resist those protons coming into the soil solution. Does that make sense? Yes? Go. This is basically referring to both of them, but really it's talking about the CEC, the exchangeable acidity. Okay. Yeah, that makes sense? Okay, did anybody have a question about this? Because I want to take the next step, which is actually talking about buffering. Okay, now imagine we have 2 soils. Okay, and one soil we have this really big CEC, high base saturation. One is we have a small CEC, and it doesn't matter if we have high base saturation because we have a very small pool Okay? If I have a really well buffered soil and I start adding soil protons basically to it, so this is the amount of protons down here, or the amount of bases that are added off of this neutral point, and this is the pH of the soil. These lines represent the pHs of those soils at certain concentrations of added or subtracted protons. Okay? So if I have a well buffered soil here, high CEC, high base saturation, and I start adding protons to it, I'm going to have a very slow response pH-wise. Because for every proton I throw in there, I'm potentially going to get a base bouncing off, which means it's in a sense neutralizing that acid. It's a base cation, right? Now, if I have a soil that has this, the one on the right here, that has a very limited amount of buffering capacity, it has a small CEC, and while it may have 100% base saturation, it has a small amount of bases on those exchange sites in total. So for every one that I throw on, yeah, I'm going to get a bounce off, but I only can do it 10 times. And so as a result, I'm going to have this huge response. Okay, this black line here basically represents water, where I in fact have no buffering capacity. For every proton I add in, I basically get more acidity. I'm not going to get any kind of buffering reaction. And so as a result, the pH change is rather dramatic depending upon whether I'm adding bases or protons. Does that make sense? Buffering at the middle. Buffering in the middle is basically cation exchange. Okay? I start throwing protons in. Those protons are going to go in the soil solution. Those protons that are in the soil solution are going to exchange with the cation exchange sites. And in essence, I'm going to have a buffering reaction. Okay? The protons are going to be neutralized by the bases coming off the cation exchange sites. Okay? This is what we've been talking about for a while, but basically here's my aluminum with hydroxide. That proton hits the soil solution. That proton reacts with the cation exchange site. It's basically held and it's neutralized. Okay? You can think of all these cation, this is the clay micelles, but basically we're looking at the active pool here, but this cation exchange is going on here. If it's a proton reacting here, I'm buffering it. And it generally happens in this 4.5 to 7.5 range. Okay? Buffering at the edges, basically we're looking at buffering at higher than 7.5 and buffering at lower than 4.5. There's two different reactions that are associated with them. At the buffering at the high, it's basically a calcium carbonate reaction. Okay? Now remember this reaction because this is the reaction of water. And we're going to take a first step. CO2 with water basically makes carbonic acid. It's a weak acid, so only one of the protons dissociate. It's a strong base. Okay? But this strong base can react with calcium. Okay? Basically, the calcium will react with this base. Okay? And as a result, I'm going to be putting in two protons into the soil solution. So when the pH starts getting higher, I'm going to start seeing more calcium in the soil solution. This calcium will react with this carbonate base, and it will knock that proton off. In essence, neutralizing the raising of the pH. Because it's going to make a calcium carbonate, and as a result, I'm going to get these two protons. Does that make sense? The byproduct of it is water and CO2. We started with water and CO2, and we end with water and CO2. No? Kind of? All right. Let's take a step back and let's think about where this comes into the system. Okay. I have a high pH. My soil has a high pH. What does that mean? Well, it means I probably have high base saturation, right? So my colloid, and we'll stop after this and I'm going to kick you guys out. Okay, my colloid on the exchange sites probably has a lot of calcium. High pH, right? I have a rainwater scenario, H2O plus CO2, all right, makes carbonic acid, H plus HCO3, right? This proton goes into soil solution. What happens to it? Potentially, it's going to be reacting. Okay? means that calcium is now going into soil solution. And even if it doesn't, because of the high base saturation in these systems, I probably already have calcium in soil solution. So what's going to happen with this carbonate? This calcium, strong reaction with this base, basically making calcium carbonate. As a result, I'm releasing 2 protons. Those 2 protons are going to go into the soil solution. What are they going to do to the soil solution's pH? They're going to lower it. So in essence, they're resisting that pH change. They're making it more acidic. Okay, because of this carbonate reaction with the calcium forming calcium carbonate. It's a buffering reaction. It's resisting the pH change. Make sense? Questions? This happens at the high end pH range because I need to have the presence of this, or potentially magnesium, but we'll talk about that at a different time.
This has been a production of Cornell University, on the web at cornell.edu.